Welcome. In this session, we'll continue with the discussion on how to use Laplace transform to solve circuit analysis to solve circuits. Let's start. So, okay. So we'll continue with the previous problem. So we have a network, series RL network. Connected to a voltage source. So value of the voltage source is 3 U of t. And this is our 2 Henry inductor, 4 ohm resistor, and our goal is to find I of t in the circuit. Now the only difference between this circuit and previous circuit is we are given that the inductor current at t equal to 0 is 5 amperes. In the previous circuit, inductor current at t equal to 0 was 0. So there was no initial condition or no initial energy stored in the circuit. But this time we are given that there is a 5 ampere current stored in the inductor at t equal to 0. So once we draw what is the first step in order to find I of t? We have to convert this into Laplace transform term. So if we try to write the Laplace transform version of these three elements, that is voltage source, 2 ohm inductor, and 4 ohm, so we have to replace them by their equivalent models. We know what's the equivalent of this 3 u of t is simply 3 by s. Similarly, the equivalent of 4 ohm is simply 4. Now, what's the equivalent of this? Since the initial condition is not 0, I of 0 is not 0. So what we'll do, we'll replace it either by this model or this model. That's called the series model or parallel model. Okay. Now, whatever model gives you the easiest solution, you'll use that. Now, if you look at this, the series model, because our goal here is to find I of t, so this series model will give us the solution very easily instead of this parallel one. We can also use this, but this model will give us the I of t very easily in the circuit. So what we'll do, we'll replace our inductor by this model. Okay. So let's draw the Laplace transform equivalent of this. So Laplace transform equivalent of this circuit will be simply, let me start with this. So we have an inductor. Inductor will be replaced by its equivalent model, and the equivalent model is inductor LS with the series voltage. This series voltage value is okay. So then we have, after this, we have a resistor, and then we have a voltage source here. Okay, so let's write the value. So what's the equivalent of 3 u of t? It will be 3 by s. What will be the equivalent of inductor? Equivalent of inductor is LS in series connected to the voltage source. This, okay. Please remember the polarity of voltage source. So we have 2 Henry. This will be 2s. Then what we have here, we have 4 ohm. And what will replace this inductor with? Inductors will be replaced by this voltage source L I of 0. I of 0 is 5, L is 2. So what's the voltage value? 2 multiplied by 5 is 10 volts. Okay. And this I of t will replace by I of s. So the equivalent model of this circuit is here. Okay. The equivalent model of this is given here. This is the equivalent model of this. So we have replaced the voltage source by 3 by S. 2 Henry inductor we have replaced it by two elements connected in series, 2S and a voltage source. Okay, because there is some initial voltage, initial current stored in the inductor, and 4 ohm resistor we have replaced it by 4. We simply write it 4. Okay. Now, as our goal is to find I of t, so we'll find first I of s. as the goal is to find I of t, we'll find first I of s. Now, if you look at this circuit, this is a voltage source, this is a voltage source, and we have two impedances connected in series. So KVL will give us the very easy solution. So if we apply KVL here, so apply KVL to this, what we have, let's start with this point and apply KVL like this. We have a voltage source and we encounter the negative terminal of that voltage. So it will be 3 by S, but negative. Why negative? Because we encounter the negative terminal first. Then we have an impedance. Impedance multiplied by current is the voltage drop. So 2S plus IS. Then we have a voltage source. The value of that voltage source is 10, and I have written minus 10. Why minus 10? Because we encounter the negative terminal first. Plus 4. Impedance is 4 multiplied by I of S. This is the voltage drop here in this 4 ohm. So, okay. All right. So now sum of these voltages will be equal to 0. That's the statement of KVL. All right. Now we'll simplify this. So let's apply. So we'll take 3 minus 3 by S minus 10. We'll take on the right hand side, and IS will here. So we'll say 2S plus 4 times IS will be equal to 3 by minus 3 by S becomes plus 3 by S plus 10. Okay, on the right hand side. Okay, now simplifying this, we can write it as I of S will be simply equal to 3 plus 10S divided by S into 2S plus 4. So this term I have written on the right hand side. That will be in division on the right hand side. So this is our current. Okay, so our goal here is now to find I of t. In other words, we have to apply the Laplace, this inverse Laplace transform to this expression. All right. So what we'll do, we'll apply, in order to apply inverse Laplace transform, what we'll do, we'll first take this 2 out from this. So let's see what happens here. So I of S will be equal to 3 divided by 10S by 2 into S plus 2 once you take 2 out from this braces. So what will be left? So if we divide the numerator by 2, we'll be left with 1.5 plus 5S divided by S into S plus 2. Okay, this is our equation. So now what we'll do next? Next, what we'll do, we'll apply this partial fraction expansion to this, right? We have two terms in the denominator, so we'll apply partial fraction expansion. So partial fraction expansion of this will be simply A divided by S plus B divided by S plus 2. Okay, this is the partial fraction expansion of this term. So this is the partial fraction expansion step. Okay, our goal is to find A and B. In order to find A and B, what we'll do, we'll cross multiply this equation, or we'll multiply simply both sides by this denominator S into S plus 2. So what we'll have, we have 1.5 plus 5S will be equal to A into, once we do the cross multiplication, it will be A into S plus 2, B into, okay. All right. So to find A, what we'll do, we'll put B equal, S equal to 0. So to find A, put S equal to 0. So what we'll have on the right hand side, 1.5 plus 0 will be equal to A into 0 plus 2 plus B into 0. So this will be B into 0. So from this we'll get 1.5 will be equal to A into 2. This implies A will be equal to 1.5 divided by 2, that is 0.75. Similarly, in order to find B here, so to find B, what we'll do, we'll put S equal to -2. So put S equal to -2. What we have from this, so we'll say 1.5 minus 10 will be equal to A into 0 plus B into -2, right? So if you simplify this, this will be 8.5 will be equal to A M0, that is 0, minus 2 into B. So what will be the value of B? So B will be simply 8.5 minus and minus will cancel. So this will be 4.25. Okay. All right. So, substituting the value of A and B back here, what we'll get IS as? So I of S will be simply A is 0.75 divided by S plus B is 4.25 divided by S plus 2. Okay, so now we know what is the inverse Laplace transform of 1 by S, and we also know the inverse Laplace transform 1 by S plus 2. So writing the inverse Laplace transform here. So inverse Laplace transform I of t will be I of S will be I of t, that will be equal to 0.75, and inverse Laplace transform 1 by S is U of t plus inverse Laplace transform of 1 divided by S plus 2 is e to the power of minus 2t U of t. Now you can take U of t outside. So I of t will be equal to 0.75 plus 4.25 e to the power of minus t multiplied by U of t. Okay, so this is the answer to this problem. Our goal was to find the current in the inductor that is flowing here, given that initial current stored in the inductor is there. So we have used Laplace transform method to solve this problem. So what we did, we first converted the circuit into the equivalent Laplace transform version. That this is the equivalent Laplace transform of this. Then we applied KVL in order to connect I of S in this equation. So this is our KVL. Now then after this, after finding I of S, we did some manipulation, that is in order to find the Laplace transform of this equation, we write the partial fraction expansion, then we find these coefficients A and B. Once we have found these coefficients or residues, then we'll get finally the current in the okay. Now, once we apply this Laplace transform, the analysis becomes very easy. It is as like we are doing the DC analysis. Okay, all these elements are replaced by their corresponding impedances, and whatever techniques that we have learned for these resistances are now valid for these impedances. 2S, 4 are here simply impedances. Okay, we'll continue this discussion in the next session, how to apply Laplace transform.